So I'm going to talk about instrumental variables. So this is sort of the third lecture on evaluation type problems, and I'm going to talk about instrumental variables and sort of do this in settings where we want to, like in the unconfounded in this case, allow for a lot of heterogeneity. And so so here's the outline. I'll talk a little bit about, I'll give some introduction, talk a bit about the basics, talk about local average treatment effects, where the key result is going to be that even if the key assumptions are satisfied, instrumental variables is very rarely going to give you the average effect for the whole population. It'll essentially only do so in two cases. One, when the effect of the treatment is constant, and that's a very strong, very difficult to believe assumption, as well as in settings where the instrument is extremely powerful, which is a result known as sometimes as identification at infinity, where you have an instrument that is so powerful that it moves the probability of receiving the treatment all the way from 0 to 1, which essentially means that for some subpopulation you have a randomized experiment, and so that's clearly also a very rare occurrence. So in most cases, at best we can estimate the effects for some subpopulations, and we'll talk a little bit about that and sort of characterize that subpopulation and see what we can learn about that. I'll talk a little bit about when there's at least some credibility to extrapolating that to the population. I'll talk sort of about more practical problems of how to incorporate covariates, what to do in settings where there's multi-valued instruments or multiple instruments, and I'll talk a little bit about the case where the endogenous regressor is not just binary, but takes on more values, and how some of these results extend. And so here, let me summarize the main points. So the key, one of the key results in the recent literature is that if we allow for heterogeneity, for which there sort of both is a lot of empirical evidence that there is heterogeneity, as well as concern that just the assumption of having a constant effect is very dubious. If we're outside of that setting, then instrumental variables still estimates average effects, but the specific average depends on the choice of instruments. And so the key theme is going to be that if you were to do this using two different instruments, you might get different results. Not so much because because one of the instruments is not valid. Even if they're both valid, they may just be estimating averages for different subpopulations. And so doing the type of specification tests where you, based on over-identification coming from multiple instruments, doesn't really work in this setting, because one of the assumptions that is being maintained, if you want to test the validity of the instruments, they said the effect is constant. Absent that assumption, two different instruments can just estimate different objects. And so then, in general, the terminology for the subpopulation where we can estimate the average effect is that these are the compliers, sort of coming from this canonical example where you have a randomized experiment with non-compliance. Some of the individuals who are assigned to the treatment don't take it. Some of the individuals who are not assigned to the treatment still manage to take it. And the ones in the middle who do as they're told, in fact, sort of who always do as they're told, who comply, whatever their assignment is, will be referred to as the compliers. And that's going to be the subpopulation that instrumental variables is estimating the average effect for. And so there's nothing, in a simple setting with a binary instrument and a binary endogenous variable, there's nothing much you can do about it. That's the only subpopulation you get, and if that's not the one, then the one you want, you may have to learn the one you get to like the one that you get, and we'll think a little bit about whether we can extrapolate from there. But so the first part is really about thinking what that subpopulation looks like and how you can characterize it. And so the setup, like in the unconfound in this case, is going to make it, it's going to keep very separate so the substantive assumptions that theory may help us with, that are all in the form of, that are pretty much all in the form of conditional independence assumptions from functional form assumptions, and as well as extrapolation. So that's really the main sort of large part of the progress that's been made in this literature sort of in the 90s. So let me just briefly remind people sort of the standard setup. So we're going to do this in a case, but for the time being, we're going to ignore the covariates, ignore any additional exogenous covariates. We're going to look at a case with a single endogenous regressor that is binary and a single binary instrument. So in this case, the standard instrumental variables estimator, so you can do that with two-stage least squares or liminal. Everything's just all going to give you the same because we're in the just identified case. What those estimators look like is the ratio of sample covariances. And in the limit, what they're estimating is the ratio of population covariances. You can get the large sample, the approximate large sample distribution from this by using the delta method. You're going to get asymptotic normality for both numerator and denominator. And the ratio will be reasonably well approximated by normal distribution as long as the denominator is not too small. Now, that's sort of a little quick. The denominator not being small will be the part of one of the Wednesday lectures. We talk about weak instruments. There's been a considerable concern with the properties of these methods when the instruments are relatively weak, in the sense that they're only weakly correlated with the endogenous regressor. I'm not going to talk about it now. And sort of partly on Friday, I will also make the point that in the just identified case, that is actually not that big a concern. That's a much bigger concern in the over-identified case. But so what I just described was the standard setup, or the standard estimator. I want to go back to this potential outcome framework for setting this up in order to formulate the critical assumptions. So that's going to start again with two potential outcomes, y0, y1, one for each value of the treatment. W is the value of the treatment, and what we observe, the outcome we observe is y1 if w is 1 and y0 if w is 0. But now the first innovation is that we do the same thing for the level of the treatment. We're going to think about there being two potential outcomes for the level of the treatment, WI0 and WI1, representing the values of the treatment given the two values for the binary instrument. So one example that I'll use repeatedly and sort of give some numbers for it in the end is Angrid's draft lottery example. So there the instrument is whether you're draft eligible, whether you have a low draft lottery number. We'll make that binary. So you're either draft eligible, you have a low lottery number, or you have a high lottery number. W is an indicator for whether you serve in the military. So WI0 tells you for a particular person whether that person would have served had they had a high lottery number. So if this person had a high lottery number, they would not have been draft eligible. They would not have been drafted. WI0 tells you whether that person would have served or not in the military. And WI1 tells you whether that person would have served had they had a low lottery number, had they been drafted. And so what we actually observe is only whether an individual served or not in the military, and what their draft eligibility status was. So we observe WI, which is W1 if C is 1, and W0 if C is 0. So what we observe here, and it's still abstracting from any covariates, is an instrument, it's a binary instrument, CI, a binary treatment, WI, which is WI evaluated at CI, and the outcome YI, which is YI evaluated at WI evaluated at CI. And what we're going to be interested in is comparisons of YI1 and YI0. So the key assumption, and I actually want to do it in two ways, but so first let me set it up this way. One way of formulating the assumption is that the instrument is independent of all these potential outcomes, these four potential outcomes in this case, YI0, YI1, WI0, and WI1. And so this really captures two parts of the assumption. That's why I'm going to break it up in a second. So the first is that it requires that the instrument is as good as randomly assigned. That it's and so in a lot of examples, like a randomized experiment with non-compliance, and the draft lottery example, that seems that's very credible. In those cases, there actually was physical randomization, so that part of the assumption is very credible. But so this way of formulating the assumption already embodies a second assumption that is substantively very different, namely that the instrument doesn't directly affect the outcome. And so in that sense, it's actually useful to split that up a little bit and in effect extend the notation a little bit. So instead of starting with these two potential outcomes for Y1, Y0, let's think of there being four outcomes, yi indexed both by the instrument and the treatment. So yi of C is 0, W is 0 corresponds to the outcome that you would see if this individual was not draft eligible and didn't serve. And the other three combinations similarly. Now, formulating the assumptions this way is a little easier, but there's some cost to that, and so let me actually first do the assumptions and then come back to that. Now we can split this assumption up in two parts. One is that we have random assignment, that the instrument is independent of all these of the six potential outcomes. That's very credible here if you actually have physical randomization. But now that's not enough. In addition, we need this, what is called here the exclusion restriction, that yi of C and W is the same as yi of C prime and W for all values C prime and W. So what this is really saying is that for any individual, changing their C doesn't change their outcome if we keep them at the same level of the treatment. And so the reason that the awkwardness in formulating the assumption this way is that it's a little hard to think about how you keep the treatment constant if you change the instrument. But that's sort of partly reflecting the fact that we don't need this assumption to be quite so strong. We're going to need this only to hold for some subpopulations, and for those subpopulations, this is not going to this awkwardness doesn't arise, as we'll see in a second. But the big advantage of formulating the assumptions in this separating the assumptions in this way, it is very clear what comes from the randomization, namely the guarantees assumption 2 here, and what is meant by saying that the instrument doesn't directly affect the outcome. What that really refers to is the effect of a manipulation that changes only the instrument but doesn't change the level of the treatment. And the key assumption there is that doesn't affect the outcome for any units. And randomization per se doesn't have any bearing on that assumption. that is a substantive one that isn't necessarily satisfied in these non-compliance examples, or even in the draft lottery example. And I'll come back to arguments why that assumption may not be satisfied there in a little bit when we'll look at those data. But given this setup, a key feature is that it's important to think about individuals' responses to the instrument. And the way to capture that is to think about a pair of values, WI0 and WI1. Both of these are binary, so that gives us 4 different groups. So in the draft lottery example, the top left group, which is described here as never takers, individuals who wouldn't serve in the military, irrespective of what their draft lottery number would be, irrespective of whether they were draft eligible or not, they wouldn't serve in the military. So you could imagine these could be individuals who were medically unfit to serve in the military, where irrespective of what their lottery number was, their lives wouldn't really be affected, and certainly their veteran status wouldn't have been affected. The bottom right was described as the always takers, individuals who serve in the military irrespective of their lottery number. Again, it's sort of there. You can think of that in the Angrist draft lottery example as volunteers, people who were willing to serve in the military and didn't really need to pay any attention to their draft lottery number, who would just go ahead and sign up. Last 2 groups are the most interesting ones. The W0 is 0, W1 is 1 group described here as the compliers. These are individuals who would not serve if they had a high enough lottery number and were not draft eligible, but they would serve in the military if they got a low lottery number and did get drafted. So for them, clearly the draft's going to have a big effect. If you have a high enough number, you get out okay. If you get a low enough number, you would end up serving in the military. The last group is what is called here the defiers. These are individuals who do exactly the opposite. If they had a low lottery number, they would they would get drafted. They would manage to get out of it. If they had a high lottery number, they wouldn't get drafted. They would volunteer. And so this group will play, sort of in this particular example, this group will play a very important role in the sense that we're going to rule out the presence of such units, of such individuals. And that's sort of very credible here. That's not necessarily so credible in other cases. So one example would be if you have a random sample of individuals who get screened for a particular program, but you have 2 different screening people, 2 different sets of people doing the screening. You could imagine that one group is more strict and the other more lenient, and so the stricter group has leads to a lower rate of take-up of the program than the other group. But it doesn't mean that there would not be some individuals who would be taken in if they were screened by the strict group, but not by the other group, and the other way around. In that case, there might well be individuals of this type. But here, it sort of seems very plausible that if individuals were willing to serve, even if they didn't get drafted, that they would also serve if they did get drafted. And so in a lot of these examples, it's very credible to rule out the presence of defiers, and it's also very extremely useful. Before doing that, however, let me make one more comment on that. That we can't directly tell what the type of a unit is. We can rule out some types for a particular individual based on what we see about them, based on the pair Ci and Wi, but we won't be able to rule out all possible alternative types. And so without making any additional assumptions, we can for each individual tell that they belong to one of two groups. So if you see someone who wasn't draft eligible and who didn't serve, you don't know whether they would have served had they been drafted. So you don't know whether their behavior is consistent with being a complier, but it's also consistent with being a never taker. It's consistent with them not serving had they gotten drafted. And so same for the other three groups. You can't rule out. You can rule out two of the four types, but not more than that. To make some progress there, we're going to make this assumption that there are no defiers, which originally was called the monotonicity assumption, here written as W1 greater than or equal to W0. But really what it means is that we rule out this defier group. There's nobody always doing the opposite of what they're assigned to. This doesn't really impose any restrictions on the joint distribution of of this four-point support distribution of W and Z. It just rules out some of the configurations of the latent variables in that case, and so it's going to help us infer what type particular individuals are. Now, so as I described in the draft, for the draft lottery example, this assumption makes a lot of sense there, makes a lot of sense in a lot of other applications. It's also directly implied by a lot of latent index selection models. If you have a model for participation that postulates that individuals look at some threshold, and if that's positive, they'll participate, and if not, they won't. Here, with a threshold that's a linear function of C plus an additive, independent, and observed component epsilon I, then that immediately satisfies this monotonicity condition. Especially with additional covariates in this equation, it's very hard to see what else is being assumed there. And in the end, the only thing we really need is this ranking of W1 and W0. But I just want to make the point that this assumption has implicitly been made in a lot of work predating this the recent instrumental variables literature by using these selection models. Now, what is the implication of the monotonicity assumption for these compliance types? It implies that for some individuals, we can now infer what type they are. You look at the individuals for whom you see not serving in the military, even though they were draft eligible, you know they would also not have served had they not been drafted, and so they must be never takers. Similarly, if you see individuals volunteer for the military, even though they didn't get drafted, you know they would also have served had they been drafted, and so they must be always takers. And it's only the other two groups where we still can't tell what type an individual is. There's still two possibilities for their types. The second implication is, and that's a slightly more subtle implication, that given this monotonicity assumption, we can estimate the population proportions of each type. Given it, and here we use the random assignment assumption as well, but if you look among the subsample that was not drafted, that had a high lottery number, if you see the proportion of, if you look at the proportion that still serves in the military, they're all always takers, so you can estimate the proportion of always takers by the conditional proportion, by the conditional frequency. You can do the same for never takers. You can infer the proportion of always takers, of compliers, given that the three proportions have to add up to 1. So the point being, given these two assumptions, we can now estimate the different, the probability of the different types. Then the second point, and there's sort of a lot of different ways of making this point, and this is not necessarily the most elegant one, but it's a very simple one in a way. If you look at the average outcomes in the 4 groups, remember what we see is not directly the compliance types, but we see the observed treatment status and the observed instrument. We can estimate average outcomes in these groups. In 2 of the groups, that's an average for just one type, either for never takers or for always takers in 2 of these groups. And in the other 2 groups, that's a mixture of average outcomes for compliers and never takers. And given that we can estimate the proportion of the population proportions of these 3 different groups, we can then disentangle these mixtures and infer what the average value of the outcome is for compliers given the treatment, Y1, and the average value of the outcome for compliers without serving in the military, Y0. So given that we can estimate both of these averages separately, we can estimate that difference. And that's what we call the local average treatment effect, the average effect for compliers. And the other part of that, sort of that's less clear from this calculation, but in sort of fairly simple algebra, you can show that that's the same object as what is being estimated by the standard instrumental variables estimator, this ratio of sample covariances. So let me step back and sort of summarize these 2 points. One is that we can actually estimate an average effect here, sort of under these assumptions, namely the average effect for compliers. And second is that standard instrumental variables actually delivers that object. Typically, sort of traditionally, people looked at the instrumental variables estimator sort of in this linear model setup where they assumed that the effect was constant. Then obviously that point is very immediate. But even if you're not willing to make that constant effect assumption, which clearly has very little credibility, then it turns out you still get a very well-defined average, namely the average for the compliers. And I suppose it's also very clear that that's the only thing you could possibly hope to get. The defiers have been ruled out by assumption. Always takers are only observed receiving the treatment. And so it's very hard to imagine that any credible way of estimating the average effect for always takers that doesn't rely on extrapolation. In some sense, you could do the thought experiment, but suppose we actually could observe directly what the compliance status was of each individual. At that point, these assumptions would correspond to having unconfoundedness given the compliance type, but you would have some groups for whom the probability of treatment was either 0 or 1, and so there would still not be anything you could do other than putting them aside and acknowledging that you couldn't estimate the effect for these groups. The final comment here is that there's no particular reason why this would have been the effect of the most substantive interest it's sort of partly this subpopulation is determined by the instrument, but it is the only one you can get without extrapolation in this case with a binary instrument. Okay, but so what else could you do here other than reporting the effect for compliers. Even though you can't directly estimate the effect for never takers or always takers, we do get you can estimate what the average outcome is for these other groups, at least under one level of the treatment. And so one thing that is useful to do, and I'll illustrate that in a little bit using the Angris draft lottery example. One thing you can do is compare these outcomes for these non-compliant groups with the corresponding outcomes for the compliers. So you can compare how different never takers are from compliers without the treatment. You can compare the average of Y0 for never takers with the average of Y0 for compliers. And similarly, you can compare the average of Y1 for always takers with the average of Y1 for compliers. It's sort of clear that the more different these groups are, the less credible it is to interpret, to extrapolate the effect for compliers to these other groups. Now, the other side isn't necessarily that if these averages are the same, that you can necessarily extrapolate things. But if you find that systematically the average outcome for never takers is the same as the expected value of Y0 for compliers, and you find that sort of both overall as well as for various subpopulations, at some point it clearly becomes more credible to interpret the effect for compliers as that for the overall population, or at least for the population also including never takers. And so we'll look at that with these draft lottery data in a minute. Second set of extensions I want to discuss here is sort of how to use covariates here. So traditionally, sort of a standard instrumental variables with two-stage least square setup, you would just include additional covariates additively and linearly in the regression, and then sort of combine whatever the original instrument was with these exogenous covariates. And that's sort of a very, at some level, that's a reasonable thing to do, especially if the instrument is independent of the other covariates anyway. However, it seems slightly at odds with this focus on allowing for a lot of heterogeneity in the effect of the treatment. So if you want to take that further, you may also want to have more heterogeneity in the correlations in the effects of the covariates on the treatment. And so I'm going to look at two ways of doing that. One sort of the more traditional Heckman selection type setup, and so this is kind of put in this potential outcome framework here. You can think of the selection equation describing the participation in the program, where you add the covariates into this latent index model, as well as an outcome equation where you add the covariates linearly as well. And so the traditional version of these models would have joint normality, and you can sort of relax various parts of this model. In some sense, what I find most concerning in this type of models is that it really imposes a lot of restrictions that are more difficult to free up on the relationship between the compliance types and the outcomes. So one way of seeing it here is sort of is that this scale, that sort of the heterogeneity of the types is really captured by this single, by the scalar unobserved variable eta I, where individuals with very low values of eta never participate, and this would correspond to never takers. With intermediate values of the covariates would correspond to compliers, and with high values of eta I would correspond to always takers. So combined here with this linear, this constant correlation and between the two unobserved components, it's going to imply that the compliers are sort of in between never takers and always takers. And there's no particular reason why that should be true in the data, and there's no particular reason to impose that in the data. In the draft lottery example, it's in the draft lottery application. In fact, if you look at this, you'll see that compliers do better than never takers under the null, but compliers also do better than always takers given the treatment. And there it's sort of very credible that compliers are a relatively more highly educated group who may have higher earnings potential than either of these other groups. And this ranking of the groups in terms of participation, so this setup where the compliance types are always ranked in this particular way wouldn't allow for that type of correlation. So an alternative way of setting this up that sort of doesn't impose any restrictions sort of beyond the exclusion restriction and the random assignment assumption is just think directly of modeling the outcomes of the potential, directly modeling the potential outcomes given the covariates. So here we have these three different types: never takers, compliers, always takers. Never takers are only observed in the W0 state. Always takers are only observed in the W1 state, and compliers are observed in both states. So so in principle, you have four outcome distributions for these four pairs of W and T. So one way of approaching this is to set up a reasonably flexible model for these four outcome distributions and combine that with a discrete response model for the compliance type. And then so here I just use a simple trinomial logit model, but you can make that as flexible as you want. And in principle, there are no restrictions being imposed here other than smoothness. You could just do maximum likelihood here and get potentially a much richer set of estimates coming out of this, where you would be able to get separate estimates depending on the covariates, as well as so you would be able to get separate effects of the treatment depending on the covariates in a very unrestricted way. And so even though this type of likelihood function may look very intimidating, there's actually a fair amount of structure on it that allows for fairly straightforward implementation of this using EM algorithm type methods or Bayesian numerical methods, which I'll be talking about tomorrow. But so, summarizing this this discussion, traditionally, covariates in these models have been added just additively and linearly. With a reasonable amount of data, you might want to do this in a much more flexible way, taking account of the structure, the mixture structure implied by the theoretical model, namely the three types of the three compliance types, and free up the distributions for the potential outcomes. Okay, so let me illustrate some of these things with using Engrist's draft lottery example. Taking some of these data, so here the interest is in the effect of serving in the military. This is data from the Vietnam War. The outcome of interest here is log earnings at some subsequent date. If you look at simple OLS estimates, you get the numbers there at the top of the slide. you get a negative but insignificant effect of serving in the military. So Angus and some people, some others, I think before that, looked at, well, not for earnings though. So Angus looked at the lottery number as an instrument for veteran status here. So if you look at the number of individuals with a high and low lottery number, as well as individuals who served and didn't serve in the military, you see that individuals with CS1, so who were draft eligible, were much more likely to serve in the military. So that's the 865 relative to 1915, were much more likely to serve than individuals who were not drafted. Under the assumption, the monotonicity assumption, you can estimate the proportions of the different types, ruling out defiers. So you end up estimating that the proportion of compliers is about 12%, compared with 69% never takers and 31% always takers. Now, this slide gives you the average outcomes in the four groups by treatment and instrument status. And so here in the 0,0 cell, we get the average in the 0,1 cell, we know that these individuals are always takers, so we can estimate directly from there what the average outcome is for always takers given the treatment. That's 5.4076. Similarly, in the 0,1 cell, we can estimate we know that all these individuals are never takers. We can estimate what the average outcome is for never takers without the treatment. The other two groups are these mixtures of compliers and never takers in the 0,0 group, and mixtures of compliers and always takers in the 1,1 group. But now, given that we know the proportions of the different types, we can disentangle these mixtures, and we can get the following estimated average outcomes for by compliance type. So there's no defiers. We got the average outcome for always takers and never takers directly from two of the cells. We disentangle the mixture, and we get the average outcome for compliers under the two different levels of the treatment, with the difference equal to minus 23%. And you would have gotten this number directly by just doing two states least squares. So the part of what you get out of doing this, so in this seemingly more indirect way, is that you also get to compare the actually, let me just go back 1 second. You can compare what the average outcome is without the treatment for never takers and compliers. And you get to see what the average outcome is given the treatment for compliers and always takers. And so the first thing you see here is that the compliers have much higher earnings than the never takers, sort of without serving in the military. The compliers' earnings are actually higher by 29%. So these groups are clearly very different. And so extrapolating the effect for compliers to that for never takers is clearly not particularly credible here. Compliers and always takers are much closer, but even there you see that compliers have considerably higher earnings than always takers. So even there the extrapolation may not be very credible. The other point, and I sort of made this earlier, is that this if you use a standard selection model, kind of using normality and additivity, the implication would have been that if compliers have higher earnings than have higher average outcomes than never takers, they should have lower average outcomes than always takers in the other treatment status. And here you see the opposite. You see that compliers actually do better than never takers when they're comparable to them, and they do better than always takers when they're comparable to them. So here, the compliers earn more than any of the other groups when they're comparable. And more generally, there may not be a restriction you really want to impose a priori. Okay, so let me make a couple of comments. So let me talk about two extensions. First one is the case where we have more than one binary instrument. We can do that in two ways. We can just think of having a single instrument that takes on more than two values. Now, in principle, we can estimate, we can define this local average treatment effect for any pair of instruments. So we have C1, two values, C1, C0. We can look at the average effect for individuals who would participate given C1, but not participate given C0. And if we have more than two of these pairs, we may get a different effect for any particular combination. And so sort of, at least for a while, it was popular to test the validity of instruments by what is implicitly just comparing different estimates based on different combinations of the instruments, that essentially tests whether these objects are equal for different pairs. And if you feel very strongly that the effect should be constant, that's a perfectly fair interpretation. But if you're concerned that there may be variation in these effects, then that leads to a different interpretation of rejections of those tests. The other thing you can do is now combine all these different instruments in various ways. So one way is thinking about what would actually happen if you use a particular function, g of c, as an instrument in a linear instrumental variables estimator. It turns out what you get is a weighted average of all these local average treatment effects with a particular set of weights. And so choosing a single function of the instrument essentially corresponds to choosing these weights. And you may try to be more sophisticated about choosing these weights, but in the end, there's nothing you can do in terms of going beyond these particular local average treatment effects. The only thing you can do is just choose their weights differently. But you're not changing which subpopulations you can get things for. In the end, the biggest subpopulation you can get the average effect for is the one where you take the instrument that gives you the highest probability of participation and the value of the instrument that gives you the lowest probability of participation, and using that binary pair as a binary instrument gives you the largest subpopulation. But you can use various other weighting schemes to up or down weight particular subpopulations. So that's closely related to some work that Heckman and Fiddlersell have done. Essentially what they do is look at the limit of these local average treatment effects. If you have a continuous instrument, you could imagine looking at these average effects, looking at closer and closer pairs of instruments. In the limit, you would get the average effect for individuals who would change their treatment status if you move the instrument up by an infinitesimal amount. And so that's denoted here by tau sub c. You can relate that, and so this gets closer to what Heckman and Fiddlersell call the marginal treatment effect. They set up a latent index model where the treatment status is equal to an indicator that some function of the instrument plus an unobserved component is greater than 0. And so you can define they define their marginal treatment effect as the average effect conditional on this unobserved component, and that directly relates to this limit of local average treatment effects for a particular value of this unobserved component. Now then, you can characterize any particular average, say the population average effect, in terms of these marginal treatment effects. But again, it doesn't change what is actually identified unless the instrument moves the probability of receiving the treatment all the way from 0 to 1. There's always going to be some marginal treatment effects that you cannot identify. And in fact, this is somewhat restrictive in the sense that you don't need to be able to estimate all the marginal treatment effects separately in order to be able to get the overall average. Because just a single binary instrument that moves the probability all the way from 0 to 1 would give you the overall average without giving you any of the marginal treatment effects. But where this is helpful is that it allows you to characterize a lot of average treatment effects in terms of this marginal treatment effect. Okay, so let me then make a couple of comments about another extension. What happens if we do go back to the binary instrument case, but the endogenous regressor is not binary, takes on multiple values. And so the main result I want to discuss here is what the interpretation is in that case of the standard instrumental variables estimator. Making the same type of assumptions as before, that all the potential outcomes are independent of the instrument, and making a monotonicity type assumption that increasing the instrument may increase the level of the endogenous regressor, but doesn't decrease it. You can show that the instrumental variables estimand, so this ratio of covariances, estimates the weighted average of unit level increases in the treatment. So now we get two types of averaging going on. Before we just had the average effect of the treatment for a particular subpopulation. Now we have a similar expression at all levels of the treatment. So the example I'm going to use in a minute is returns to schooling example. So Yij minus Yij minus 1 is the effect of an additional year of schooling for a particular individual. We get the average of that for the subpopulation for whom the instrument changes you from a particular level of schooling to below J to a level of schooling above J. So that's the first type of averaging. And then we weight all these this unit level average effects by a set of weights, lambda J, where the bottom of the slide gives the representation for this lambda J. And the key point is that these weights add up to 1 and are non-negative. Okay, let me illustrate this using this returns to schooling example where Engers and Kruger estimated the effect of schooling using quarter of birth as an instrument. It's a paper that sort of motivated a lot of econometric theory the last 10 years because it's also pretty much the basis of the weak instrument literature. But using this as a single instrument case, there's no concern with the weak instrument problem. And so they find a small correlation between education and quarter of birth. They find a small, but again significant correlation between earnings and quarter of birth, and they interpret the ratio of that as an estimate of the returns to schooling. So in this particular case, it's clear that the instrument is relatively weak, that there's only few individuals affected by this. So maybe it's sort of interest to look at what the subpopulation actually is that is affected by this, and what the particular average is that we're getting here. And so here are some figures that are intended to illustrate it. The histogram at the top is just the distribution of earnings in this data set. So you get a lot of individuals at 12 years of education. There's a smaller mode at 16 for college. If you look at the normalized weight, so that they integrate out to 1, what you see is that the instrumental variables estimate sort of gives you a weighted average of unit level increases in education, where the particular year that's being averaged over is actually remarkably spread out. There's considerable weight, not just on very low levels of education, but it goes up almost to 16, which is somewhat surprising given the nature of the instrument here. So this may actually indicate other concerns with using this quadrat of birth as an instrument here. But if you take these numbers at face value, it suggests that the compulsory schooling laws didn't just change people by moving them from 10 to 11 years of education, but it actually moved some people from whatever level they had before. It encouraged some people to increase their levels of education beyond 15 or 16. The other point is that if you look at the unnormalized weight function, which is just the difference in the distribution functions, you see that the size of this complier subpopulation here is incredibly small. In the end, there's only a very small subpopulation that is affected by these compulsory schooling laws. And so even if the instrument is valid, even if all the other concerns are taken away, then this is a subpopulation that is potentially very different from the population at large. Now, it may very well be a very interesting subpopulation for policies that involve keeping people in school longer at low levels, but it certainly is a very small subpopulation, and concerns about extrapolating this to other subpopulations are probably more severe here than in other applications. Okay, I think this is pretty much right on time. So actually, let me see if there's any questions. Sorry. Yes?
I've got a question about when you have the dividers, you assume that they're zero?
Sorry.
When you assume the dividers are zero in the treatment report?
Yes.
So how large can that number actually be in truth?
Well,
what percentage of the sample could that be, the true dividers?
So in fact, that's not all that critical an assumption. If without that assumption, what is being estimated by instrumental variables is a weighted average of the effect for compliers and defiers, the weights still add up to 1, so that's all nice and well. The only problem is that the weight for the defiers is negative, and so it could have, if there's a very large group of defiers, it could be that both for compliers and for defiers, the average effect is positive, but you could be estimating a negative effect because the weights are just very far from outside 0 and 1. So in some sense, this is not a critical assumption, nowhere near as critical as the exclusion restriction, but it significantly simplifies the interpretation.